Okay, can you hear me? Yeah. I'm Manolis Papastergis. I'm very happy to be here. It's my first time in Santa Cruz, and now you can see my full title. It's about Too Big to Fail with H1 Kinematics of Field Dwarfs. So let's start that. What is the too big to fail problem? Some people in here know that better than me, but there's a lot of confusion in the community, and I can tell from the referee reports I get on my fellowship applications. So the too big to fail problem is basically the statement that is very difficult to explain both the abundance of dwarfs and their internal kinematics within lambda CDM. Okay? And this explains also the confusion because it has to do something with the number of dwarf galaxies and something with the internal kinematics. So it's kind of like half of the missing satellites, missing dwarf problems, and half the cusp versus core. But it's not exactly either of those problems. Okay. So how does that work? Let's go back to the beginning. This is the missing satellites problem that everyone knows and loves. So there are tons of small subhalos in cold dark matter, not many galaxies observed. But basically, the problem with the missing satellites problem is that it's not very difficult to solve. Actually, I can solve it just by looking at this picture without knowing almost any physics. How that works is like this. So I see about 20 galaxies there. I see kind of 20 big subhalos there. So why don't I put those galaxies there? Okay. Then the very small stuff will be killed by ionization feedback, and the other stuff I just haven't discovered yet. Okay, so I just need to be patient. So very nice solution, very believable. So I believed it when I first heard it. Okay, but let's go and see if that actually works. Okay, let me take those subhalos and draw the rotation curves down, and then let's go to the actual satellites that are supposed to live in there, measure their kinematics. This is what they look like. Okay, so if I want to explain why there are very few galaxies, I mess up their kinematics. On the other hand, there are subhalos that matches their kinematics, but there are very many. So I'm going to mess up their number density. Okay? So this is, I cannot get them both right in cold dark matter. So any solutions? As soon as the too big to fail was proposed, millions of solutions came about. And whether you like too big to fail or whether you don't believe in too big to fail, you have to appreciate that every proposed solution has boosted research in that specific area in our community. Okay, so it's a huge driver of research, the too big to fail problem. The first solution had to do with the Milky Way, okay, problems with the Milky Way. Maybe the Milky Way halo is lighter than we thought. This turns out that it would alleviate the too big to fail problem. Or maybe, the Milky Way is one system where we found this problem. This is statistics of one. So maybe the Milky Way just has an atypical satellite system. It turns out that the too big to fail problem exists also in Andromeda. Okay. So already these solutions may be true for the Milky Way, but it turns out they don't give the too big to fail is more general than them. So when it was realized that both the Milky Way and Andromeda have this problem, the attention went towards satellite processes, things like tidal stripping. Okay. This is a great plot that shows this. This is a dark matter only run of a satellite next to the Milky Way. It turns out that when you include hydro processes, the Milky Way has a disk and so on and so forth, tidal stripping is more effective. You can actually decrease the dark matter mass of a subhalo. You can explain those puzzling low velocities that you see. Okay? This is similar work based on Apostle simulation. The problem here is that people have studied, except for satellites now, also small dwarfs, isolated small dwarfs in the local group. And it turns out they have very similar properties. So you cannot tell, except for the color, you wouldn't be able to tell on this plot here which ones are the isolated dwarfs and which ones are the satellites. Okay? And in fact, when you do a proper analysis of too big to fail with isolated objects, you find that too. Okay? So satellite processes are also not a general solution. They might be there, but the too big to fail problem is also found for isolated dwarfs. It turns out that it is found not only in isolated dwarfs in the local group, so very near the Milky Way and Andromeda, but also in the local volume, okay? Within 10 megaparsecs. as Ferrero 2012 shown, and also my own work has shown. The same exact problem. So it turns out that too big to fail refers to all galaxies, satellites of at least 2 systems that we know about, isolated in the local group, and field galaxies in the local volume. It's very general. So people started to look for similarly very general solutions, solutions that can apply to any kind of dwarf, whether it's a satellite or isolated. So the most promising solutions are the so-called baryonic solutions, and have to do with things like ionization feedback. Maybe you kill some galaxies from forming. Baryon depletion, in a hydro run, you eject most of the baryons, so the mass of your halo shrinks compared to a dissipationless simulation where all the dark matter is around. And core creation, that we heard a lot about in the previous 3 talks. Okay. So reionization feedback. So there is there's a widespread belief in the community that reionization feedback helps you solving the too big to fail problem. Turns out this is not the case. And it is not my own research that says that, but is the research of the articles that are associated with this explanation wrongly. So here is work by Zavala 2016 with the Apostle simulation, and he shows how you have the dark matter only halo velocity function in gray, and then when you add hydro effects, this is the velocity function that you get that nicely passes through the data points for the Milky Way satellites. But it turns out that the reionization is this part of the effect. Okay? It is just killing small systems. You flatten out your velocity function. As you can see, this flattening has nothing to do with explaining the observed kinematics of dwarfs. It is actually baryon depletion plus stripping, the only effect that can possibly help you in resolving this issue. Okay? So reionization feedback does not help you in solving the too big to fail problem, and this is because it is seen in relatively large dwarfs. It is not an ultra faint problem. Okay? It is baryon depletion and stripping that can actually lower the mass of those systems. So here you see quite a big shift in the velocity function. This is because not only you have baryon depletion, but also stripping, and this helps move the dark matter only curve towards the observation. But in the field, the effect is much smaller because the stripping effect is gone. So when you assess this same problem in the field, you can look that this effect, baryon depletion, is not enough. Okay? So this is what the rotation curves of halos expected hosts look like in dark matter only, and baryon depletion brings them down. Indeed, you have made them lighter, but it's not enough to explain the very low velocities seen for dwarfs in the field. What about core creation? Core creation is very, very promising. I don't need to talk about it. You heard a lot about that. This is very nice work by Aaron Dutton, with the Nihao simulation. This shows the too big to fail problem with isolated dwarfs in the local group, similar to Shea Garrison Kimmel. And it shows that once you include core creation, you can very nicely explain the observed kinematics of those dwarfs. And this is because you basically, by creating a core, you move mass outwards, the enclosed mass drops, and the velocities drop, explaining the very low rotational velocities observed for dwarfs in the local group. So does that work for all kinds of galaxies? So it turns out it's not easy to test core creation as a solution too big to fail. You have 2 avenues. One is you go down in stellar mass, as James said, because there you don't have enough energy to produce cores. But there's also another avenue. You can try to measure the kinematics outside the core region. Cores are about 1 kpc. So if you go to 2-3 kpc and you measure the kinematics, the core should not be there. So this is what I did, and for that you cannot use stellar kinematics, because stellar kinematics are by definition confined to the stellar disk, which has the typical size of the core. So this is a comparison of, again, Nihao rotation curves. You can see that the curves in the middle explain very nicely the kinematics of dwarfs with small kinematic radii within 1.5 kpc. The problem is that also when you go outside of 1.5 kpc, you see the same typical velocities very low. Okay? So you can see that the kinematics look very similar even when you go outside the core region. Now, this does not necessarily disprove cores and so on, because there are selection effects that go into these samples, possible observational errors, and so on and so forth. But it's something very important to keep in mind. Okay? It is measuring the kinematics at large radii gives you a way to test core creation in hydro simulations. Now, are there any other solutions? One important thing that has came about very recently are possible observational effects. What happens here is that these systems here look like nice data points with nice error bars. You know, no one would get suspicious about them. But you can go and look at the data, what they look like. And this is like this. This is Leo P, about 2 megaparsecs away, very low mass galaxy. Now, you tell me what the inclination of this galaxy is. Okay, because I have to correct the observed velocity for the inclination. So you may be doing serious errors in the inclination estimate. The problem is that you need to be doing serious errors for all of these guys, and this is not easy. Okay, so inclination errors could provide a solution, but I'm not very optimistic on that personally. Another more serious issue is that you know, this velocity field here is not great. Okay, you see some general gradient, but you know, it's not the most good-looking velocity field you'll ever come across. And then the problem becomes: do H kinematics trace the true potential? Okay, am I having a true representation of the underlying enclosed mass? So this could give a very nice explanation, because basically, if your H1 kinematics do not trace, you can just be biased by 10 kilometers a second, which is not a huge amount, and would explain all of this range of observations. So this is some very, very preliminary work from some galaxy simulations from Robert Verbeke in Ghent in Belgium. And what you can see here is that when you measure the true circular velocity curve, this is the red line, when you go and measure the H1 rotational velocity, appears to be much lower, okay, in very scattery, messy kind of velocity field. So this is a very, very promising way to explain this effect, and quite simple. Now, what's the problem here? Yeah. The problem is that also all of the other solutions to the too big to fail problem were very reasonable and looked very promising. Okay. But it turns out that many of them we were able to disprove them after we looked for more ways to test them. Okay. So we would like to do the same for this one. Okay. We would like to test in practice whether this effect is there. So that's going to turn out to be very, very challenging, because the problem is that this circular velocity curve, you can do it very easily in a simulation, but is unobservable in simulation. Okay? So given a dwarf on the sky, how do you tell if it's H1 kinematics trace or do not trace the true potential, which you cannot measure? So if you have any good ideas, please let me know. Okay, I'm also thinking very hard. Another issue is that if this effect is there, if the H1 kinematics don't trace the true potential, a lot of the observational evidence in favor of cores is gone, because you don't need a core anymore to explain this kind of slowly rising rotation curves. Okay.
Give us an idea what's going on.
Okay. Yeah. And another is basically because of the feedback. Well, I'm saying in this simulation, I'm not saying that this feedback is correct or not, but I'm saying in this specific simulation with the feedback that they have, the velocity field becomes very messy. And this is...
Messy is already included in observation.
Yeah, the line widths, right? The line widths are here. Okay.
I'm looking on the website.
That's right. Yeah. The problem is, could those galaxies with these observed velocities and these line widths live in these kinds of halos? I'm not saying that this is the case for sure. We need to test it, but
You cannot hang there without any support. Right? No way now. You need to have some pressure support. So what happens? Are you plotting only rotation velocity, or are you plotting total line width on the left side?
on the left side, this is only rotational velocity.
What total?
That's right. That's right. This is this preliminary work. Will
Then you move it.
okay, okay. But what I'm saying is that it is very important to understand under which condition this happens, and does the feedback implementation have to do with this effect? And it will be great to test it observationally, but it's going to be very, very challenging. Okay, any good ideas are highly appreciated. Okay, let me conclude. What is the too big to fail problem? It is just the statement that it's difficult to explain both the number densities and the internal kinematics of dwarfs within lambda CDM. It was first identified for the satellites of the Milky Way, but now we know it is true for all dwarfs, including isolated and filled ones, and any proposed solution has to be valid for all dwarfs. What about solutions? In the beginning, it was thought it was something strange with the Milky Way. Perhaps something has to do with satellite processes. It turns out that's not the whole story. I'm not saying these are wrong, but it's definitely not the whole story. Baryonic solutions are very promising. They're based, reionization doesn't help, but baryon depletion and core creation do. And with present data, it is not entirely clear that these effects can fully solve the problem because of the measurement of velocities outside of the core region. The too big to fail problem would be solved if the H1 kinematics wouldn't trace the underlying enclosed mass, but this will be very, very difficult to test observationally. Thank you.
Could you please explain how it's possible to explain that problem with the co-creation? The co-creation, the co is about 1 kiloparsec side, right?
Yeah.
Your measurement, co-creation doesn't remove mass. Mass is preserved,
Yeah.
right?
Yeah.
So, and you observe that your galaxy at a 4 kiloparsec. So you move half kiloparsec mass to 1.5 kiloparsec mass. Doesn't change whatsoever your maximum velocity. So
Yeah.
Can
this
it
is-
possibly solve the problem?
That's right. I mean, this is why those curves are above the points, right? Because you can.
One would want you to use it as an explanation.
Because I cannot guarantee to you. So because these H1 kinematics for now are just a compilation from the literature, I cannot guarantee to you that these are typical galaxies. Okay. But in the future, we'll have blindly selected samples, and this will help this problem. No, I agree with you. I agree with you. I'm just saying that at present, someone could tell me, okay, these are strange objects because of the way you selected your sample and so on, and I cannot exclude it. But, yeah.
Do we have other questions? Yeah, be loud so everyone can hear you.
Okay, sorry.
Down on batteries.
Can you clarify what you mean by baryon depletion, change of Vmax?
Yeah.
You simply mean just remove some of the baryonic mass?
Yeah, exactly. Exactly.
Repeat the question.
Yeah, it asks what I mean by baryon depletion. So in a dissipationless simulation, everything is dark matter. So it sits there in the halo, doesn't go anywhere. But in a hydro simulation, the baryons can be kicked out of the halo, and this decreases the mass. Okay, even if you don't form a core, regardless, you decrease the mass. But this is not a big effect because you can at most eject 1/6 of the total mass. That's how much you have to work with.
Okay, any final questions? No, let's thank him again.
Thank you.